Previously, we defined the natural exponential function as the exponential function whose derivative is equal to itself. So let's practice using this derivative formula. For instance, now if we want to take the derivative of e to the tan x power. So what we'll do is we'll take the derivative of e to the tan x by applying the chain rule. So it'll be e to the tan x. We leave this part unchanged. Basically, the derivative of e to the x is e to the x. So the derivative of e to the tan x will be e to the tan x times the derivative of tan x. Right, so there we're applying the chain rule. And the derivative of tan x we know is secant squared. So this will be e to the tan x times secant squared x. And yeah, so basically we're applying the chain rule that we see here. If we've got some function u in the power, then the derivative of e to the u will be e to the u times the derivative of u. Here, let's practice again with the product rule now. We've got e to the negative 4x times sine of 5x. So of course here we're going to have to use the product rule. So let's write out what it'll be here. It'll be the derivative of e to the 4x, or e to the negative 4x, times sine of 5x without taking a derivative, plus e to the negative 4x times the derivative of sine of 5x. Okay, so here you see we've applied the product rule. And we know that the derivative of e to the negative 4x will be e to the negative 4x. And then applying the chain rule, we'll have multiplied by the derivative of negative 4x will be negative 4. And then times sine of 5x. Okay. And then here we'll have e to the negative 4x times the derivative of sine of 5x, which we know that will be 5 cosine of 5x. And so here let's just rewrite this as negative 4e to the negative 4x sine 5x plus 5e to the negative 4x times cosine 5x. So we can leave it like this. You could also rewrite it with the factor of e to the negative 4x factored out. So we have e to the negative 4x times negative 4 sine 5x plus 5 cosine 5x. Now suppose I want to find the absolute maximum and minimum values of the function f of x equals x e to the negative x. So what we'll need to do is essentially find the critical points of f and then determine whether those critical points tell us where our maximum or minimum is located. So let's see what our critical points are for this function. So again, we're going to apply the product rule. So we've got the derivative of x will be 1 times e to the negative x without taking a derivative, plus x times the derivative of e to the negative x will be e to the negative x times the derivative of negative x, which will be negative 1. So here I can again factor out e to the negative x, and that leaves me with 1 minus x. And then setting this equal to 0, I can get my critical numbers. In this case, e to the negative x will never equal to 0. That's always positive. 1 minus x will equal to 0 when x is equal to 1. So we have just this one critical value at x equals 1. Let's test the behavior of f prime on the intervals that are greater than 1 or less than 1. So for instance, if I evaluate f prime at a value that's greater than 1, say x equals 2, f prime will be negative there, right? We can see that e to the negative x will always be positive, times 1 minus something greater than 1 will of course be negative. On the other hand, we see that if I choose a value of x that is smaller than 1, say x equals 0, we'll get a positive value. So that shows us our function will be increasing on the interval from negative infinity to 1, and then it'll be decreasing on the interval from 1 to infinity. So that clearly we're going to have an absolute maximum value at x equals 1. And let's plug x equals 1 into the original x, or into the original f. So that gives me e to the negative 1. So that's our absolute maximum. And the question is, what would our absolute minimum be? Well, in this case, it appears that because we've got a function which is going to be negative when x is negative, that goes so graphically we can imagine that as x goes to the right forever, we get something that's going to approach 0, because one way I might visualize this is you've got x over e to the x. As x goes to infinity, e to the x is going to grow much more rapidly than x. So this is going to approach 0 as x goes to infinity. But what about, on the other hand, as x goes to negative infinity? What happens there? As x goes to negative infinity, well, then you've got something in the numerator that approaches negative infinity, and something in the denominator that approaches 0. Which means this is going to blow up in the negative direction. So in the case as x goes to negative infinity, this will go to negative infinity. In either case, there's no absolute minimum. We can imagine the graph maybe looks something like this, where it reaches that peak at x equals 1, but as it goes to the right, it'll tend towards 0, and as it goes to the left, it'll go to negative infinity. Here are some basic properties of e to the x, which, if we notice, is essentially inherited from the fact that e to the x is just an exponential function with a base that's greater than 1. Here we remember that e can be approximated with something around 2.71. So we can inherit the properties of b to the power of x, where b is a base that's greater than 1. Okay, so we know graphically it might look something like this, where it goes to infinity as it goes to the right, and it goes to 0 as it goes to the left. So yeah, as x goes to infinity, it approaches infinity. As x goes to negative infinity, it approaches 0. Let's think about how I would find the limit of a function like this. E to the 2x over e to the 2x plus 1. One trick that might be helpful here would be to divide out e to the 2x from the numerator and denominator. In other words, I can multiply 1 over e to the 2x in the top and the bottom. Now this is a little handy trick that will help us evaluate this limit, because now I've got 1 over 1 plus 1 over e to the 2x. And if I look at just this term here that's left, you got 1 over something that approaches infinity. So this is going to go to 0. So we're left with 1 over 1 plus 0, which is 1. How would I sketch the graph of this function e to the 1 over x power? So we could go through a bunch of steps here to analyze it in a lot of detail. So we can focus on some of the important details. One important detail is to think about its domain. Since it's got 1 over x in the power, it'll be undefined at x equals 0. But otherwise, it will be defined. So the domain will be all x other than 0. Now we can also think about when the function is increasing, when it's decreasing. We can also think about what its x and y intercepts may be. In fact, let's figure out what its intercepts are first before we start analyzing its derivatives. By setting x equal to 0, we get its y-intercept. In this case, doesn't exist. So no y-intercept. And we also notice that e to the 1 over x is never going to equal to 0. So there's no x-intercept. Okay, so that's actually interesting, because now we can think about how we can sketch the graph when there's no intercepts. Another thing we may consider now is when the function is increasing or when it's decreasing. So let's take f prime. And for this function, we'll have e to the 1 over x times the derivative of 1 over x. So 1 over x is like x to the negative 1 power, so that'll be negative x to the negative 2 when we take its derivative. Or here we can write this as e to the negative 1 over x over negative x squared. And, well, when will this be positive and when will this be negative? What I notice is that because e to the negative 1 over x is always a positive value and x squared is always a positive value, this will always be negative for all x. So that means that f is always decreasing. So at this point, we've gathered a bunch of information, but it's perhaps a little bit difficult to think about where the function is able to be graphed. Well, one other thing we can consider are any vertical or horizontal asymptotes. For instance, I noticed that it will have a vertical asymptote at x equals 0. And I know this because as x approaches 0 from the right, 1 over x will be going to infinity, which means that e to the 1 over x will also go to infinity. How about as x approaches 0 from the left? Well, if it's approaching 0 from the left, then 1 over x goes to negative infinity, and therefore e to the 1 over x will go to 0. How about as x goes to infinity? So what are the horizontal asymptotes? Horizontal. So when I take the limit as x approaches infinity, well, I get something in the exponent that is going to 0. So it's going to be 1. And notice this would be the same as the limit as x approaches negative infinity, because you get again something that approaches 0 in the exponent. So this is perhaps going to give us the most information about our graph, because now we've got at least some guidelines for how to graph it. So we know it's got this horizontal asymptote at y equals 1. It's got a vertical asymptote at 0, because as it approaches from the right, it's going to blow up. And then it'll approach, as it approaches 0 from the left side, it'll approach 0. So we think from the left side, it's perhaps going to look like this. And then from the right side, it's going to follow those vertical and horizontal asymptotes. Notice here, putting a hole at 0, because of course the function is undefined at 0.